Welcome back to Programming Fluency. This is section 8.2, calloc, realloc, and patterns. Last time you used malloc to allocate a block whose size you fixed once. In this video, you will learn to allocate zeroed memory with calloc, resize a block with realloc, and build an array that grows on demand. Let's begin. Welcome back. In the last section, you used malloc to allocate an array whose size you chose at runtime, but that size was still fixed for the array's whole life. What if you do not know how many values you will need? A log reader processes lines until the end of the file. A game tracks enemies that spawn and die unpredictably. In this video, you will meet two more allocation functions. Calloc, which gives you zeroed memory, and realloc, which resizes an existing block. And you will put them together to build a dynamic array that grows on demand. This is the plan for this video. First, calloc, which allocates memory that is already zeroed for you. Next, realloc, which resizes an existing block, moving it in memory if it needs to. Then the safety pattern. You use a temporary pointer so a failed resize cannot lose your data. After that, the dynamic array, an array that grows by doubling its capacity. Finally, why we double. Doubling the capacity keeps appends cheap on average. Let's set up the two problems this section solves. First, malloc gives you one fixed block, but many collections grow while the program runs, and you cannot predict the final size. Second, malloc leaves the memory full of garbage, whatever bits were already there. For numeric arrays, you often want every element to start at 0. Picture a dynamic array as an expandable shelf. You start with a small shelf. When it fills up, you request a bigger shelf, copy everything over, and the old shelf's address may become invalid. That copy and move is exactly what realloc does. First, calloc, which stands for contiguous allocate. It differs from malloc in two ways. It takes the element count and the element size as two separate arguments, and it sets every byte to 0. So malloc of 5, sizeof_int gives you 5 integers full of garbage. Calloc of 5, sizeof_int gives you 5 integers all set to 0. Both reserve the same memory. Calloc just zeros it for you, saving an initialization loop. Now the definition. Calloc of count, size allocates count elements of size bytes each and zeros them all. Free it with free, just like malloc. There is a bonus safety feature. Because calloc receives count and size separately, it can check whether multiplying them overflows and return null if it does. Malloc of n times size can silently overflow before malloc ever sees the value. So calloc is the safer choice for untrusted input sizes. So when do you reach for calloc versus malloc? Both allocate the same number of bytes. The difference is the starting state. Use calloc for counters and accumulators, where every element should start at 0. Use malloc for an array you will immediately fill, because zeroing is wasted work if you overwrite every element anyway. Use calloc for an array of pointers that should start as null, since null is 0 on all common systems. And use calloc when the size comes from untrusted input, because it detects the multiplication overflow that malloc cannot. In short, if you meet a known 0 starting state, or the size is untrusted, choose calloc. Otherwise, malloc is fine. Second, realloc, which stands for reallocate. It changes the size of a block you already have. You pass it the old pointer and the new size, and it returns a pointer to the resized block. Here we start with 3 integers, 10, 20, 30, then grow to 5. Ignore the temp pointer for a moment, we will come back to it. The first key fact. Realloc preserves your existing data, so 10, 20, and 30 are still there. The second key fact: the new slots R of 3 and R of 4 are uninitialized. Realloc does not zero them, so you must write to them before reading. It also may move the block to a completely new address, which is why we do not just reuse the old pointer blindly. So what does realloc actually do? This flowchart shows that it tries 3 strategies in order. First, extend in place. If there is enough free space right after the current block, realloc just moves the boundary. No data is copied. This is the fast case. Second, allocate copy free. If the block cannot grow in place, realloc allocates a brand new block, copies your existing data into it, and frees the old block. The returned pointer is a different address. Third, fail. If no block of the new size is available, realloc returns null, and it leaves your original block untouched, so your data is still there at the old pointer. The big implication is case 2. The returned pointer may differ from the pointer you passed in, so you must always use the value realloc returns. Now back to that temp pointer. The most dangerous mistake with realloc is assigning the result directly to the same pointer, like R equals realloc of R. Why is that dangerous? If realloc fails, it returns null, and that null overwrites R. But the old block was not freed, so now you have lost the only pointer to it. In one line, you both lost your data and leaked the memory. The safe pattern uses a temporary pointer. Write temp equals realloc of R, then check temp. If it is null, handle the error and R still points to the old block, so you can free it or keep using it. Only if realloc succeeded do you write R equals temp. This pattern is non-negotiable. Now for the payoff. Combining malloc, realloc, and free, you can build an array that grows as needed, a dynamic array. This is the structure behind Python's list, C++'s vector, and Java's array list. The idea is to track 3 things next to the data pointer. Data is the pointer to the heap array. Count is how many elements you are actually storing right now. And capacity is how many the array can hold before it needs to resize. The logic is simple. When count is less than capacity, there is spare room, so appending is cheap. When count equals capacity, the array is full, so you realloc to grow and then append. This is the heart of the dynamic array, the append function. It takes a pointer to the array struct and a value. First it checks, is count equal to capacity? If yes, the array is full, so we grow. We compute a new capacity of twice the old one and call realloc with the temporary pointer pattern. If realloc fails, we return -1 and the old data is safe. If it succeeds, we update the data pointer and the capacity. After the growth check, whether or not we grew, there is now room. So we store the value at data of count and increment count. Notice the doubling new cap equals capacity times 2. That is the key to good performance, and we will see why in a moment. Let's watch the array grow. It starts with capacity 4. The first 4 elements fit with no resizing. The figure shows 3 strips. The top strip is full, 4 of 4. The middle strip has doubled to 8 with 3 spare cells in gray. The bottom strip has doubled to 16 with 7 spare cells. When the 5th element is added, count equals capacity, so append doubles the capacity to 8. At the 9th element, the capacity doubles again to 16. So the array grew from 4 to 16, holding 10 elements with only 2 reallocations. The gap between count and capacity is spare room, ready for future appends without any copying. Why multiply the capacity by 2 instead of adding a fixed amount like 10? The answer is total work. Suppose you add 1,000 elements one at a time. With linear growth, adding 10 each time, you copy the whole array about 100 times, and each copy is bigger than the last. That is about 50,000 elements copied, and the cost grows like n squared. With doubling, you copy at sizes 4, 8, 16, and so on, only about 8 times, totaling about 1,020 elements copied. The cost grows like n. So doubling does more work per resize, but resizes far less often. The total cost of n appends is proportional to n. We call this amortized constant time. Any multiplier greater than 1 works. The one rule is, never grow by a fixed additive amount. Let's revisit the most important bug in this section, because it is worth repeating. Assigning realloc directly to the only pointer, r equals realloc of r. If realloc fails, it returns null, and that null overwrites r. Realloc did not free the original block, so it is still allocated, but you have just thrown away the only address that pointed to it. In one line, you lost your data and leaked the memory. The fix is the temporary pointer pattern. Temp equals realloc of r. If temp is null, free r and handle the error because r still points to your data. Otherwise, r equals temp. Always use a temporary. A second realloc bug, using a pointer that pointed into the old block. Here we allocate 10 integers and save a pointer called middle to element 5. Then we realloc to 20 integers. Remember, realloc may move the whole block to a new address. If it did, the old block was free, but middle still points into that old free block. It is now dangling, and reading star middle is undefined behavior. The fix is to recompute any derived pointers after every realloc. So after r equals temp, you would set middle equals ampersand, r of 5 again, computed from the new r. The rule is simple. After realloc, treat every old pointer into the block as invalid. Let's recap. Calloc and realloc complete your dynamic memory toolkit, and together they build the dynamic array. Calloc of count. Size allocates zeroed memory and checks for multiplication overflow, which makes it safer than malloc for large or untrusted sizes. Realloc resizes an existing block and preserves your data, but it may move the block to a new address. So always use a temporary pointer with realloc, so a failed resize can never lose your data. The dynamic array tracks 3 things: data, count, and capacity, and it doubles the capacity when full. Doubling gives amortized constant time per append, far better than linear growth. Next, your dynamic array stores integers. To reuse the same code for doubles, chars, or structs, you will learn void star, a generic pointer, and function pointers, which let you pass behavior as an argument.